At 120 feet beneath the surface of a major metropolitan downtown, the overburden pressure exerted by soil, water, and structural foundations reaches 85 psi, equivalent to 12,240 pounds of continuous downward force per square foot. To advance a horizontal void through this geological matrix without triggering a catastrophic surface subsidence crater, an earth pressure balance tunnel boring machine must continuously generate over 63 million pounds of forward thrust while maintaining pressure equilibrium to within a tolerance of plus or minus 1.5 psi. A modern mega-TBM is not merely an excavator. It is a sealed, mobile subterranean factory, weighing up to 15.4 million pounds and spanning over 400 feet from the cutting face to the trailing gear. This machine executes 5 simultaneous thermodynamic, structural, and mechanical operations: rock fracture, hydrostatic pressure balancing, continuous muck extraction, precast concrete segment erection, and 2-component annular grouting. The structural failure of rock does not occur via grinding or scraping. It occurs via controlled induced tensile stress under massive localized hydraulic force. The primary excavation plane consists of a welded structural steel disc weighing over 900,000 pounds. Distributed across this geometry are 19-inch hardened alloy steel disc cutters. Each individual disc cutter is engineered to withstand a static continuous point load of 65,000 pounds of force directly against the rock face. As the machine drives forward, the cutter head rotates between 0.5 and 2.5 RPM. The disc cutters roll along concentric circular kerf paths. When 65,000 pounds of normal thrust is applied through the tapered edge of the cutter ring, it penetrates the rock by 0.2 to 0.5 inches per revolution. This creates a localized compression zone directly under the tip. When the compressive stress exceeds the yield threshold of the rock, often surpassing 30,000 psi, shear cracks propagate laterally toward adjacent kerf tracks, causing large rock chips to detach through tensile failure. To overcome the dynamic frictional resistance of several hundred cubic yards of pressurized earth contacting the cutter head, the main drive system must deliver up to 35 million foot-pounds of continuous breakout torque. This rotational power is transferred through a 26-foot diameter, triple-row cylindrical roller bearing. This single component must simultaneously absorb 3 structural forces: the 63 million pound axial thrust reaction, radial shear loads from gravitational cutter head sag, and immense overturning moments caused by heterogeneous rock-to-clay geological transitions along the cutting face. In soft ground tunneling beneath the water table, unconstrained excavation causes immediate hydraulic collapse. The engineering countermeasure is the earth pressure balance principle. Directly behind the cutter head lies the excavation chamber, separated from the atmospheric sections of the machine by a 2.5-inch thick structural steel bulkhead. The volume of excavated spoil within this chamber is maintained under direct mechanical and hydraulic pressure, matching the natural in-situ geostatic and hydrostatic ground pressures ahead of the machine. Raw excavated soil is rarely a stable fluid medium. To transform erratic gravel, sand, and clay into a homogeneous plastic, impermeable paste, high-pressure conditioning systems inject chemical conditioning agents at rates up to 500 gallons per minute. Biodegradable surfactant foams, expanded with compressed air at an expansion ratio of 10:1, are injected through the cutter head face at 90 psi. In abrasive sand matrices, high molecular weight polymers and sodium bentonite slurries are added. This reduces internal friction, lowers cutter wear by up to 60%, decreases shear strength, and forms an impermeable paste that prevents groundwater inflows up to 87 psi. Pressure regulation is closed-loop and continuous. 9 piezoresistive pressure sensors, distributed across the pressure bulkhead, measure the internal muck matrix at 100 millisecond intervals. If excavation chamber pressure drops by as little as 2.0 psi below the calculated ground target, automated control systems throttle back the extraction rate of the discharge mechanism, preventing surface settlement that could destabilize overhead skyscrapers or utility corridors. extracting hundreds of tons of pressurized material per hour from an 85 psi environment to an ambient 14.7 psi atmospheric tunnel environment without losing face containment is one of the most critical hydrodynamic challenges in mechanical engineering. The solution is a variable speed, continuous flight screw conveyor driven by dual hydraulic motors delivering 450,000 foot-pounds of torque. The screw conveyor achieves a controlled pressure drop along its 45-foot casing entirely through internal shear resistance and frictional drag between the soil plug, the outer steel casing, and the rotating flight ribbons. As the solid shaft rotates between 5 and 22 RPM, the volume of material transported is precisely calibrated against the forward advance of the machine. If the volume extracted exceeds the volumetric advance of the shield by more than 2%, it indicates subterranean over-excavation, a precursor to ground collapse. The entire system is monitored by continuous belt-scale nuclear density meters and laser volume scanners, accurate to 0.5% volumetric displacement. From the discharge gate, the depressurized spoil transfers onto a continuous trailing conveyor belt system rated at 2,500 tons per hour, spanning miles through the completed tunnel back to the surface staging portal. To generate 63 million pounds of forward thrust, the TBM relies on a ring of 56 double-acting hydraulic cylinders operating at fluid pressures up to 5,000 psi. These cylinders do not push against the surrounding earth. They push directly against the leading edge of the precast concrete tunnel lining already erected behind the shield. Once the machine advances the precise width of one ring, typically 6.0 feet, propulsion temporarily pauses. The mechanical vacuum erector, moving across 6 degrees of freedom, lifts precision-manufactured segments from the interior delivery bed. Each concrete ring consists of 7 to 9 segments, plus a final trapezoidal keystone. Cast from steel fiber-reinforced concrete with a 28-day compressive strength exceeding 8,000 psi, each segment is manufactured with dimensional tolerances tighter than 0.04 inches. Along every segment edge, continuous dual-lip EPB-TBM elastomeric gaskets compress as the segments are drawn together. This creates an immediate, hermetic seal against both hydrostatic pressure and methane gas ingress. As the tail of the shield advances, it leaves an annular void of 5.5 inches around the outer perimeter of the concrete ring. To prevent any ground relaxation, a two-component mix, composed of cement bentonite slurry and a sodium silicate accelerator, is injected directly through the tail skin at 105 psi. The mixture gels within 12 seconds, locking the precast ring into structural solidarity with the surrounding geological strata. Behind the primary 45-foot shield sits the trailing gear, a continuous multi-deck train spanning over 400 feet. This structural assembly houses the electrical infrastructure required to power the machine's multi-megawatt demand. High-voltage trailing cables feed 13,800 volts AC to onboard step-down transformers, powering 45 separate hydraulic power units, water chillers processing 600 gallons of cooling fluid per minute, and massive ventilation ducts delivering 45,000 cubic feet per minute of conditioned air to the working face. Steering a 15 million pound machine with millimeter precision demands optical laser guidance, combined with ring laser gyroscopes. A motorized total station mounted to the cured tunnel ceiling continuously tracks an active target on the machine's main bulkhead. By computing spatial coordinates at 10 Hz, the navigation computer detects positional deviations smaller than 0.05 inches. Steering adjustments are executed not by mechanical rudders, but by differentially modulating hydraulic cylinder stroke lengths across the 4 quadrants of the propulsion ring, carving sweeping 800-foot horizontal curve radii through solid ground. Operating invisibly beneath active municipal foundations, the tunnel boring machine resolves the ultimate geotechnical contradiction, exerting millions of pounds of destructive mechanical force to disintegrate solid rock while maintaining delicate thermodynamic and hydraulic equilibrium against the weight of the earth itself. It is a monumental achievement of structural engineering, precision fluid mechanics, and automated subterranean manufacturing.